A very commonly used routing protocol in Cisco-based networks is Enhanced Interior Gateway Routing Protocol, or EIGRP. We are going to talk about how EIGRP forms and maintains neighbor relationships. We are going to talk about how these neighbors exchange the information, how they exchange the routes. We are going to talk about the best path selection and load sharing supported by EIGRP. And finally, we are going to address the summarization and filtering in EIGRP. Before we dive into the details and explore EIGRP greatly, let's take a quick overview of what EIGRP actually is. EIGRP is a Cisco proprietary advanced distance vector routing protocol. Now, the words advanced distance vector and Cisco proprietary do warrant some explanation in this case. Cisco proprietary usually means it's reserved for use only on Cisco devices and those vendors that actually license the technology from Cisco. But in case of EIGRP, this is how EIGRP started its life. Relatively recently, I believe in late 2012 or 2013 even, there has been a series of RFCs published that detail the open operations of EIGRP, opening the possibility that EIGRP might be implemented by some other vendors not directly licensing the technology from Cisco. This is good news because EIGRP is overall, relatively speaking, good and reliable protocol. It does have certain shortcomings when it comes into network visibility and what information it maintains about the entire network, but it's very, very fast and very agile. It's a very good protocol to use. So why do we call it advanced distance vector? Well, here we have to mention a little bit about the history of EIGRP. EIGRP didn't used to be called advanced distance vector. Cisco called it the hybrid routing protocol. The idea behind this hybrid notion was that EIGRP kind of marries the best of distance vector worlds, the simplicity and the speed of distance vector routing protocols, with the knowledge and the neighbor maintenance operations of link state routing protocols like OSPF or ISIS. However, there was really nothing hybrid about the behavior in EIGRP. What EIGRP did was operate in distance vector operations while maintaining the neighbors and maintaining high degree of reliability in that neighbor relationships. So that's important thing to understand. But why do we call it advanced distance vector? Well, for two reasons. One is that obviously we are maintaining the neighbor relationships. We are not going to blindly send or receive routes from just about anyone. We are going to first form a neighborship. We are going to agree on certain parameters in that neighborship, in that relationship, and only then we are going to accept and exchange the routing information. And this routing information is then going to be used to calculate the best paths throughout our network. And instead of using a simple metric like, for example, hop count, which is in use by RIP, EIGRP uses something that we call the composite metric. The composite metric consists of several different values. For example, bandwidth, delay, reliability, and load are some of the parameters that make up the composite metric, which is then passed through relatively complex metric calculating formula using constant modifiers called K values, and the end result is relatively large number that represents our metric. So this is what makes EIGRP advanced distance vector routing protocol. I'll talk about EIGRP metric in a little bit more detail a bit later on. The second bit that makes it advanced is the neighbor discovery, and this is where the hello protocol comes into play. Hello protocol simply means that we are going to be sending certain messages on the link. Apologize. We're going to be sending certain messages on the link, and we're going to be expecting those same messages coming back to us and by other neighbors, and we are going to form some sort of a two-way communication. We are going to know that neighbors are there, and if we don't hear from them for a certain period of time, we are going to declare them as non-operational, and we are not going to be maintaining the routes that we learn from them in our database and routing tables. So this is what the neighbor discovery is all about. Again, I'm going to talk about this in a little bit more detail later on. Then we can have the topology information exchange or the routing information exchange. In EIGRP, this could be a full route exchange. It means that one neighbor is sending to other neighbor its full routing table, or a partial. If a certain thing has changed, the route has changed its metric or the new route has shown up, or maybe we need to remove a route. This partial information can be communicated, unlike some other routing protocols which send only full updates, like for example RIP. And finally, the best route selection is also what makes up the advanced part of EIGRP. With EIGRP, we have really two branches of decision-making process when we are selecting the best route. One is the local decision. Can we immediately use this route? Is this the best route we can use? Or if we have multiple alternate routes, maybe we need to speak to our neighbors first before we can use a certain route. I'll explain this in greater detail a little bit later on. But let me go back and talk a little bit about the neighbor forming process, or the discovery of the neighbors. One of the primary purposes of forming the neighbor relationship is to know on a particular network segment, are there any other devices that speak the same protocol as we do? In this case, EIGRP. This can be done using two possible methods in EIGRP. One is the automatic discovery, and the other one is manual discovery of the neighbors. Or I shouldn't really say manual discovery, but I should say manual configuration of the neighbors. Now, with automatic discovery, what's going to happen is that routers are periodically going to send hello messages. These messages, depending on the interface type, so if you have a serial interface, the timers are going to be different than on, for example, Ethernet interfaces, but we're going to concern ourselves only with Ethernet interfaces for now. So the periodic hellos are going to be sent by default every 5 seconds. Now, if we don't hear from a neighbor for a certain period of time, we are going to declare that neighbor as dead or unreachable, unavailable on this network segment, and we are going to discard information that we have learned from that neighbor. The default hold down timer or the default hold timer is 15 seconds on Ethernet, or as we can see, 3 times the hello interval. These hello messages are sent to the multicast destination, the link local multicast destination of 224.0.0.10, and they are not sent as UDP or TCP messages. They are sent with a special protocol type 88, which signifies that these messages are actually EIGRP messages. Manual discovery, or the manual configuration of the neighbors, is mostly used in network environments where we do not want the automatic discovery to work, or automatic discovery is simply not available. For example, older non-broadcast multi-access networks like, for example, frame relay or ATM come to mind here. On those network types that don't support multicast or broadcast traffic by default, we cannot automatically discover the neighbors, so we need to manually configure our EIGRP. And this is done using under the process configuration for EIGRP, which I'm going to show you in a minute, by configuring the neighbor's address explicitly. Configuring the neighbor's address explicitly enables sending unicast hellos to that particular neighbor. Now you can see here on the slide that there is a third item mentioned that I did not talk about yet, which is preventing automatic discovery. In some cases, we do want the protocol, in our case EIGRP, to be enabled on the interface so that that particular interface address or the network associated with that particular interface can be advertised into this protocol as an internal route. But we may not want to form any neighbors should there be other routers speaking the same protocol as we are on that network. We don't want to form the neighbors with those routers. If we have that situation, we are going to use a feature in iOS which is called passive interface. With the passive interface feature, we are preventing the hellos from being sent out of this interface. We are not going to be processing any incoming hellos or any incoming routing updates, but the interface network, the network associated with the interface, will be advertised into EIGRP as a protocol internal route. Last but not the least, let's take a look at the configuration examples for EIGRP. Here behind me I have 2 sample configurations. One is using the traditional configuration using what is now called numbered configuration mode, where we simply say router EIGRP and then specify the AS number in which this process is going to operate. Then we specify the network statement and specify the network range on which EIGRP is going to be active. The network statement for EIGRP comes in 2 forms. One is the classful network format, where we simply specify only the network on which EIGRP is going to run, and the other one is where we specify the network but also the wildcard mask. Wildcard mask in the case of network statements is simply an inverse-reverse net mask. Whatever is in net mask set to 0 in wildcard mask, in this inverted wildcard mask, needs to go and become 0. So 1 becomes 0, 0 becomes 1. So it's really just a inverted net mask. And then finally, we have an example here using the neighbor statement. With the neighbor statement, we have to specify what is going to be the unicast address of our neighbor, and then we need to specify on which interface we are going to have this particular neighbor. I have also used the example of passive interface here. Now, the newer configuration introduced with iOS 15 is so-called named configurations. Named configurations do allow for certain flexibility not available in the numbered configuration mode. Namely, with the named configuration, we can first of all support in the same process IPv4 and IPv6. In the previous configuration modes, we would need to run separate processes for IPv4 and IPv6. And obviously, I'm going to talk about IPv6 separately later on. Now, another very important method introduced with the new method of configuration is this AF interface command. Now, with the AF interface command, what we can do is in the process itself, we can group certain configuration parameters that would otherwise be divided into individual interface configuration modes. Things like the hello interval, the authentication modes, and so on, that would be scattered all over the configuration, now can be grouped under this AF interface subsection. If we want something to apply to all the interfaces, instead of specifying the interface name here, we would simply use the word default. So if we specify the default as the interface name, then this configuration applies to all the interfaces. So in this configuration here, what I have is router EIGRP and then the name. The name can be just about anything. And then I'm saying for address family IPv4, run in autonomous system ASN, whatever that number would be. So this here is going to be the AS number we are going to use. Then again, I can use the network statement, and keep in mind that both network statement formats are still supported with the new configuration mode, and then I can have any number of AF interface commands. And in this configuration example here, what I have done is I have said that for this particular interface, we are going to be operating in a passive mode. So pretty much I have replicated the configuration that I had here above. I briefly mentioned EIGRP authentication just a second ago. EIGRP supports MD5 authentication of all communications, and I'm going to talk about it next, but before I talk about MD5 authentication in EIGRP, I need to spend just a minute talking about one protocol-independent feature that is used by EIGRP authentication and other subsystems in iOS to provide the necessary key infrastructure used by authentication services. And this feature are keychains. So in their simplest form, keychains are an infrastructure to provide us with the possibility to use multiple passwords, to use automatic rekeying or automatic changes of passwords at specific times. Now, much more importantly, the keychain infrastructure can be used by multiple protocols. That means that we can define a keychain and then use it by EIGRP or use it by some other protocol that can use the keychains. Keychains are easily configured, easily maintained, and much more scalable way than maintaining passwords individually on each individual interface. Now, imagine that you had a router that had 10 EIGRP interfaces on which you wanted to form neighbors. If you wanted to change the password and you didn't have the keychains available to you, you would have to go on each and every one of these 10 interfaces and change the passwords, and on all of the neighbors that are using this interface. But using the keychains, what we are actually doing is on an interface, we are simply specifying a reference which local keychain to use on all of 10 of our interfaces. So if we change the keychain in one place, we have effectively changed password on 10 interfaces. Pretty cool when you come to think about it. Now, if we take a look at how the keychains are configured, it's very, very straightforward. What we need to do first is say that we are defining a keychain. So this is in line 1 of the configuration. We are defining the keychain under the name. Then in line number 2, we have to specify the key that we are going to use. Now remember that we can use multiple keys in a single keychain. So this ID here will simply be a number. In the case of MD5 authentication, as I'm going to talk about in a minute, these key IDs actually need to match on two sides that are authenticating each other. So let's say that we are specifying key number 1, then in line number 3 we specify the key string. And in this case our key string will be password. There are actually 3 different ways to specify this. We can simply say password, and we can say 0 followed by password. And this 0 here tells iOS which encryption mechanism to use to encrypt this password in the running configuration. If we use 0, we are telling iOS that an unencrypted password is following. Or we can use 7, and then there is going to be an encrypted hash. This is not usually something that you will do manually, but it is sometimes used, or not sometimes, but it is going to end up in your running configuration should you use service password encryption global command, for example. And in that case, all the passwords that were defined as plain text earlier, they're going to be re-entered in your keychain as a one-way type 7 hash. Or actually, a type 7 is not a one-way hash, apologize about that. It's a two-way hash. That means that this keychain actually can be decoded. And I will show you that as well. Finally, in line 4, we are specifying at what times or during which time is this key valid. Now, this accept lifetime actually refers to this key ID, not to the entire keychain, because we could have multiple keys defined in a single keychain. So with this accept lifetime, we are saying if we receive this password during this period of time defined by the start time and the end time, we are going to accept and treat this key as a valid key. However, in line 5, we are saying that when we need to use information from this keychain, this key ID, this key with this identifying number, will be used and sent only during the periods between the start time and the end time. Start time and the end time can be either omitted. If we don't specify them, simply we are creating a perpetual key. That means that the key is valid during all times. It can be specified in a very, very specific way. That means that the key is valid from this hour, minute, second of this particular date to this hour, minute, and second on that particular date. Or it can be set to forever. That means that we can, for example, specify start time that is very specific, and then we just say forever. And if that is the case, simply the key will be valid from this particular time here that we have specified as the start time until the end of time. Or we can specify an actual duration in number of seconds when this key is valid. Let's take a look at a couple of keychain configuration examples. In the first example here, we are defining what I like to call a perpetual key. This is the simplest form that we can use the keychain in. We are simply specifying the keychain name, and in this case it's going to be perpetual. We are specifying the key ID, in this case it will be key ID number 1. And finally, we are saying that the password we are going to be using is Cisco. Since we have not specified start or end time or accept or send lifetimes, this key is always valid. In the second example here, we are defining a keychain under the name 1, which is going to be using key number 17 with the password Cisco. However, this key is not always valid. My goal here was to create a key that is going to start being valid on January 1st, 2010 until the end of time. So I'm going to define send lifetime beginning at midnight of January the 1st, 2010, and the duration of validity is infinite. And this is the period of time from January the 1st, 2010 until the end of the time that I am going to be sending this key whenever I reference this keychain. And also I'm specifying the same thing as my accept lifetime. That means if I'm going to receive this key in any communication during this period of time, which is again from midnight of January the 1st, 2010 until the end of time, I'm going to treat this key as valid. In this next slightly more elaborate example, I'm defining a keychain that is automatically going to be rekeyed, or we want to change the password automatically that we are using on a particular day or at a particular time. But in this case, it's just going to be midnight of January 1st, 2015. So what I'm defining here is the keychain under the name 2. Remember, this 2 here can be any name. I just called it 2 because it's my second example of a timed key. And then I'm defining 2 keys. In this case, key 10 and key 20. The key string in the first example is going to be Cisco, and then on January 1st, 2015, we want to change the password to be Disco. And here in the send lifetime and accept lifetime, this is where the actual magic happens. Now, remember that in the previous example, I had a key that started its validity on January 1st, 2010. So this doesn't change. I want this key to be valid from January 1st, 2010, and then I want it to no longer be valid after the midnight on January 1st, 2015. When does the midnight begin? It begins at 000000 January 1st, 2015, which means that I'm going to stop sending key number 1 at 23:59:59 on December 31st, 2014. So at the last second of 2014, this key is no longer valid. The same thing about the accepting this key. I'm no longer going to accept it after midnight of December 31st, 2014. However, if I take a look at my key number 20 here, what's happening with that key is that the send and accept lifetimes begin at midnight on January 1st, 2015 in both cases, and these both keys are valid for infinite period of time after that. So effectively what's going to happen on January 1st, 2015, we are no longer going to be using, sending or accepting password Cisco, and we are going to be using password Disco. The third example here is going to be even more elaborate. So what I want to do here is perform what I like to call a double rekey. So what I want to do here is I want to have the key that is valid until January 1st, 2015. Then I want to start using another key, and then after a certain period of time has elapsed, I want to start using the third key. There is no particular reason that I wanted to show you this other than to show off a couple of more commands that you can use in the context of configuring keychains. So I have already explained the behavior of what is going to happen here in my key number 1 in this example. So this is a new keychain. This is keychain 3, which has 3 keys, keys 1, 2, and 3. So the first key is going to be valid from January 1st, 2010 until midnight January 1st. That's clear. The second key is going to be valid from January 1st, 2015, so this is this part, and then it's going to be valid for 129,600 seconds. So this value here is in seconds. And this, when we divide by 60 and by 60 again, this is going to give us exactly 36-hour duration. So this is going to be valid for 1 day and a half. So what we want to do here is what we want to start after at least day and a half. We want to be using a different key. But here in key number 3, we do have slight problem. The slight problem is that this key begins on January 2nd of 2015. That means that during that period of time, both of these keys here are perfectly valid to be used. We are going to be sending both of these keys, and we are going to be accepting both of these keys. This is a perfectly valid configuration. You could have that overlap. Now, should you? Doesn't matter. Depending on the protocol, how the protocol handles multiple keys is entirely up to you. But these 2 keys are valid. We are going to be sending them, and we are going to be accepting them should we receive the authentication that uses one of them. Another thing that I wanted to show you here are 3 different ways that the key string can be configured in our keychains. The first example we have already used multiple times. It's simply key string followed by the password, in this case Cisco. Now, in the second key, I have used 0 followed by disco, which basically tells iOS that an unencrypted password follows. In the third example, I have used the encrypted password, and this is indicated by number 7 here. So this string here is a 2-way hash that can be decrypted by iOS, and it can be decrypted by you. All you have to do to actually see what this password is to run a simple command. You can do command show keychain. And with show keychain, what's going to happen, you are going to see the unencrypted password here. So this is just minor encryption to prevent prying eyes from seeing that the password used here was actually Cisco Disco. And you can decode this number here and you are going to see that the password is actually Cisco Disco. Now that we learned how keychains work, we can take a step back and take a look at how EIGRP authentication is configured. EIGRP is configured in multiple steps. The first thing that needs to be configured is the keychain itself. Then, depending in which mode you are configuring EIGRP, are you using the numbered configuration mode or you are using the named configuration mode, you have to go under the interface in a case of a numbered mode, which is right here behind me. In the case of a numbered mode, you have to go under the interface and you have to specify that for that particular EIGRP process, that for that particular EIGRP AS number, you are going to be using the MD5 authentication mode. It is the only available authentication mode for EIGRP, so I don't know why Cisco insists on specifying the mode MD5, but it's there for future compatibility. Say that newer versions of iOS introduced some different authentication mechanisms, like for example SHA-1 or something along those lines. Then the next configuration line needs to be specification or the reference to the pre-configured keychain. So here is an example of what we can do. First, we have defined a keychain name, we have defined a key ID, we have defined a key string of password. Then under the interface, we are going to say IP authentication mode, EIGRP, specify the AS number that we are using, and say that we will be using MD5 authentication mode. Then we are going to say IP authentication keychain, EIGRP, specify the AS number that we are using, and the name of the keychain that we have pre-configured. Relatively straightforward. Even easier if you are using named configuration mode. Again, 2 steps that are required. First, the definition of the keychain, and second, this time under the process and under the address family, we're going to go into the AF interface subconfiguration mode. And remember, for the AF interface, we can use either the keyword default, in which case this is going to apply to all the interfaces enabled for this EIGRP, or we are going to specify interface by name. Now, using AF interface default allows us to easily configure authentication on all the interfaces enabled for EIGRP. This is not available under the EIGRP numbered configuration mode. Pretty interesting advance, if you ask me. So let's take a look at the example. Again, we are configuring keychain name, we are configuring key ID, we are configuring key string, and specifying the password. Then we are going to go under the router EIGRP name, and there is a tiny little typo there. It should say router EIGRP, but that's fine. iOS would still accept this as a valid command. So we're going to say router EIGRP, we are going to give it a name, so it can be name. We're going to say address family IPv4 autonomous system and then specify the AS number. We're going to go under the AF interface subconfiguration mode. In this case, I am using the default keyword, which means that this applies to all interfaces. And in this case, I'm going to say authentication mode, MD5, and I'm going to say authentication keychain and specify the name of the defined keychain there. As you can see, even simpler configuration when you are using the named EIGRP configuration mode.